Hello, this is the second lecture regarding refraction. So in the last lecture I told you about optical density or refractive index, and then I told you I will talk about laws of refraction so on in this lecture. So actually the topic of refractive index or optical density will not be over or not be completed if I don't mention to you guys a very important phenomena which is called dispersion. So what happens, I will talk about light, but all the phenomena of waves like reflection, refraction, diffraction, whatever is common for sound waves also. So all kind of wave, they obey the same thing. So dispersion is there in sound wave also. Now what is dispersion in light wave, I will talk about it. So what happens in vacuum, suppose light is traveling, light, sunlight, let us say. So there is no medium, so there is no dispersion. Okay, now what is dispersion, we'll talk about it. So light, like white light is made up of violet, indigo, vibgyor or vibgyor, I don't know how to pronounce it, something like that, right? So that is means no concept of color will come when the white light will travel through vacuum, because there is no medium to interact. But if you do the same thing with prism, okay, the bending effect is more in the case of prism. Then you all know this Newton great discovery that white light, and then it was split into colors. Okay, I am just drawing two things. This will be red, this will be violet, and so on. Okay, we'll talk about this. So what happens when a light meets a medium, and this medium has refractive index, right? We'll talk about, we talked about it. So this refractive index is actually somehow dependent on wavelength. Okay, so actually it is inversely proportional to lambda square. Okay, actually there is a complicated formula, but roughly you can say that n is inversely proportional to lambda. Now you all know that wavelength of red is very greater than wavelength of violet. So if you compare these two things, so this is more, so refractive index for red light is less than refractive index for violet. So actually what I wanted to say, that refractive index somehow lead to what is called dispersion. And what actually, why red light reaches here and why violet reaches here, actually dispersion is a phenomena of all waves, and it is a phenomena in which more the wavelength, more will be the light in the medium, in the dispersive medium. So inside the glass, outside in air, all the wavelengths are traveling at the same speed. As it encounters the glass, you all can see red will feel less refractive index, so it will travel fastest, and actually that's why it reaches here, right? And violet will move slowest. So inside this medium, more the wavelength, more is the speed. That is actually called dispersion. So dispersion is a phenomenon in which wavelength decides the speed. More the wavelength, more will be the speed. Okay, that is only valid inside a medium. Now medium, I am talking about dispersive medium like glass. In vacuum there will be no dispersion. Okay, now moving on, let us talk about laws of refraction in detail. So there is a first law and there is a second law. First law is also called Snell's law. Okay, so let us talk about it. So according to first law, let me draw two diagrams which I will use again and again. So suppose light is traveling from medium 1 to 2, and in this case medium 2 to 1. So let us say light is this is the normal, and it is denser medium, let us say. So this is R and this is I. Now according to Snell's law, n1 sin I will be equal to n2 sin R. This is actually Snell's law. Now sine is nothing but trigonometric function. I guess you guys know sine, tan, cos and so on. So refractive index, the product of refractive index of the first medium multiplied by the sine of the angle will be equal to the product of this into this. Right? Now if this law you are applying to, let us say this is air, this is glass. So if you apply to this case, we will get Ng sin I is equal to Na sin I Ng sin R, and sin I by sin R, I can write it Ng by Na. Now how to read these things? In general, we take refractive index of air to be 1. Okay, so we define all the refractive index generally with respect to air. So refractive index of air is taken to be 1, and this thing you should read as a refractive index of glass with respect to air. Okay, so Ng by Nga, refractive index of glass with respect to air, should read as Ng by Na. This is equal to 1, but we write it like this. So Nga, suppose you guys know it, it's 1.5. Now this also tells you that this product remain constant. Okay, this into this. Now moving on, if light is going from 2 to 1, so let us say, okay, this was denser medium. So let us say this is, okay, one more thing before I move. This angle of incidence should be measured with respect to normal. Okay, try to understand, this is not angle of incidence. Okay, sometimes you guys do this mistake, and again the angle of refraction is measured with respect to normal. Now one thing I want to talk about it is angle of deviation. This is the angle of deviation. Now can you guys calculate how much will be that? I will just write the actual value. This angle of deviation will be equal to I minus R in this case. Okay, vertically opposite angle, this total angle will be I. You guys can find this much will be angle of deviation. Now let us say light is going from second to 1. Okay, let us say this is I, this is R. Now how you will apply Snell's law here? Again you have to see from where to where light is going. So here you will write in this diagram the Snell's law. If light is going from 2 to 1, N2 sin I is equal to N1 sin R. Okay, now second law of refraction is second law of refraction says that the incident ray and the refracted ray, this is refracted ray, okay, R means ray, I am writing, this is incident ray, reflected ray, and this is normal. So second law says that incident ray, normal and refracted ray, they lie in one plane. Plane means if you take a photograph, then all will be coming in the same photograph, in one plane only, all are there. Okay, that is the second thing. Now Before I move on to the application of this, let me just tell one more thing. This refractive index or optical density, more the optical density, more slower will be the speed of light in it. But in refraction, we talked about frequency does not change. Now this refractive index depends on three parameters as given in your book. One is temperature. So with temperature, or if you increase temperature, refractive index decreases. So you guys can sort of think of it. Suppose you are if you are comparing ice and water, so I guess ice will have more refractive index than water. I, I don't know, just I'm making assumption. I don't know really. So if you are heating a thing, then refractive index decreases. Okay, whatever your book says. Second is it depends on color. I talked about that in dispersion, that refractive index somehow depends on color. If you talk about red light and violet light, since wavelength of red light is more than violet light, refractive index which the red light will suffer will be less in comparison to the violet. We talked about it in dispersion. Now next thing I'm going to talk about is called principle of reversibility. Okay, now principle of reversibility is amazing concept. Let us see whether you guys will get it or not. So I'm okay, let me draw two diagram. So this is the interface of the two medium, and this is I, this is R, this is first medium, second medium. Okay, so if light is going from, let us say, this end to this end, we can write Snell's law. So it will be N1 sine I is equal to N2 sine R. Keeping in your mind that R is measured from the normal, I is measured from the normal. Now, what will happen if we incident the light at the same angle R? Try to understand. Okay, so now we incident light at the same angle R. Okay, so this angle is same as that of this. So in this case, if we change the scenario, okay, so we incident at an angle R, and let us just imagine, okay, that this angle is I. Why this is I, we'll talk about it. So we can all write Snell's law, N2 sine R is equal to N1 sine I. Now, okay, just try to connect them. Do you think that they are identical equation? So what we have done, we have just changed the scenario here. This is the angle of incidence, this is the angle of this. Now, so principle of reversibility says that if we exchange incident and reflected light, if we exchange by keeping the angle same, so we are flipping incident ray to the this way and reflected ray to like this. So if we switch incident ray and reflected ray and by keeping angle same, light will travel exactly the same path. Okay, one way of saying is this, that if light took, let us say, some time to come from this point to this point, exactly it will take the same point for the light to go from here to here. So this is actually principle of reversibility. It says that if we switch in incident ray and refracted ray by keeping angle same, the result is same. Now this one is based on the fact that if you write here n1 by n2 equal to sine r by sine r, and this one will give you n2 by n1 is equal to sine r by sine r. Now if you can recall, if light is going from first to second, we define this to be n21. Okay, this is refractive index of the second medium with respect to this is n12, this is n12 and this is sine I by sine r, and this one will be n21 sine, this is sine r. As we did that in optical density thing also, if you multiply this and this, n12 into n21, this will give you 1. Okay. Now in the next lesson we'll talk about it, some application of refraction, and we'll discuss some numericals also. Okay, so thank you.